Okay, and I think we'll get started. Good morning. Welcome to the third day of ESWEEK. And if you don't know my name by now, I have to say it one more time. My name is Sharon Hu. I'm the general chair for ESWEEK 2023. And I'm sure you're here. That means you love this community and you did have a good time, but you still managed to get up early today. And so we had lots of exciting programs yesterday, right? I hope you were at the keynote, you were at this panel we put together, and we give out the Taste of Time Award. That was really great. The three papers are actually, it turned out, even though they are get selected separately, they are actually all interrelated. That shows what a nice, even though we have three separate conferences, it's a very nicely connected community. So today, we're going to have some more exciting events for you. And first, we're going to present the best paper and other awards. And from the best papers are from each conferences, and we have several other awards. And then we'll have the long expected keynotes from Professor Lothar Thiele. And then we'll have, of course, the conference papers and more posters. And this is not the last day of the conference. We still have 2 more days. We'll have 2 symposiums. And then we'll have a workshop tomorrow as well. And the most exciting part some of you are expecting is where 2024 going to be. You have to stay to the end of the award ceremony to hear that. Okay, with that, I think I also want to mention that we are on social media. If you haven't followed us, please do so. I think Mitra has been posting lots of exciting things. If you want to see if your picture's on there, you should try to post yourself as well, right? Okay, so with that, I'm going to bring our award chair, Laura Posey, on the podium so she can tell you all the award winners.
Thank you, Sharon. Thank you very much. I'm so glad to be here to present to you more awards. You maybe know my name also, but I'll repeat it too. Laura Pozzi from USI Lugano in Switzerland. So yesterday we gave the Test of Time Awards. Today we have several more, starting with the best papers. And we will start with cases. We had 3 best paper candidates for each conference. The program chairs are to be thanked for the selection. They put together a committee to then read the papers and also go to all presentations, and finally the committees got together to select the winner for each conference. So for cases, the winner is ZPP, a dynamic technique to eliminate cache pollution in NOC-based. I was just told that maybe the winners are not yet here. Is that correct? It is. So perhaps we'll postpone their picture to later in the ceremony, and we'll go ahead. All right, so next conference down here. Oh, because I'm holding it. Next conference is CODES ISS. And again, we had 3 candidates, and the winner selected is Florets for Chiplets, Data Flow Aware, High Performance, and Energy Efficient Networking. Congratulations. Congratulations.
Thank you.
Congratulations.
Thank you.
Congratulations. Yes. Congratulations.
Congratulations. I'll give to all the rest of you.
Maybe we'll move this side of the flowers. So,
Yeah,
you come. Okay. Thank you. Congratulations. Then we go to EMSoft, and the winner of the EMSoft conference is equation-directed optimization of vector semantics to enable optimized code validation. Congratulations. Well done. Congratulations. Oh, yeah. Congratulations for a good selection.
Yes.
I guess do we go on the other side? No, I guess we just, Sharon and I will be small. Thank you. Congratulations again. Okay, we also had Outstanding Reviewers Award. We already gave them certificates Monday night, so we will not call them on the floor, but we still wanted to congratulate them. So for cases, we have Geronimo Castrillon and Krishna Nandivada. So congratulations to them. And then Codes ISS, Francesco Regazzoni and Ryan Kim. Congratulations. Ian Soft, Taylor Johnson, and Jean-Luc Charbard. Okay, so now we want to give outstanding service. We want to thank someone here for having served in the steering committee for 10 years and having been the chair. He's stepping down. So do you know who he is? We want to thank Nikhil Dutt. Thank you, Nick. Thank you. Thank you. Thank you. And then we also want to give a special thanks and the CEDA Service Award to the General Chair of ESWEEK 22, who did a wonderful job, and we want to call here Aviral Srivastava. Thank you. Thank you. So now I would like to call Tulika Mitra, Editor-in-Chief of Text. You want the, yeah.
Thank you, Laura. So it's my pleasure to announce the ACM Text 2023 Best Paper Award. This award recognizes the outstanding paper that was published in 2021 or 2022. We had a slate of very excellent candidates, and I would like to thank the search committee chaired by Aviral Srivastava for doing a great job in going through multiple rounds to choose the best paper winner. And the winner is Event B, Hybridization, a proof and refinement-based framework for modeling hybrid systems. And we have two of the authors here, Guillaume Dupont and Yamin Ait Amir. Congratulations.
Thank you.
So with that, I would like to hand it over to Wan.
Thank you, Tulika. So now I'll be happy to announce ACM SIGBAD Paul Caspi Memorial Dissertation Award as the award committee chair. So the award 2023 ACM SIGBAD Paul Caspi Memorial Dissertation Award goes to Dr. John Oak Choi from Purdue University, US. The thesis topic is high performance and reliable intermittent computation. So we have formed a committee, and we have received a large number of high quality submissions. So the entire committee spent 6 months thoroughly and evaluating all these, reviewing all these dissertations. From the committee, you can see we have diverse technical backgrounds and geographical locations. So we performed 2 rounds of evaluation. After the first round, we selected the top 3 of the dissertations. And then in the second round, we perform voting. The review feedback will be provided for all the nominees. So because of the visa issue, Dr. Choi couldn't come today, but we have his colleague to receive the award on his behalf. Please. Thank you, Sinan. So I'll proceed to the competitions. So we have 3 competitions overall in this ESWEEK. So I'm going to start from the ACM SEEKBAD SRC. So there are 2 categories, undergraduate and graduate. Champions of both categories will compete in the ACM Grand Finals, representing the community of embedded systems, real-time systems, and also cyber-physical systems. So undergraduate category, the champion goes to Valen Yamamoto from UC Irvine. After I announce all the winners of the competition, so everyone, all the winners, please come onto the stage and then we can take a group photo. So graduate category, champion goes to Artem Klashtoni from the University of Waterloo, Canada. First runner-up, Zain Wu Abidin from Thailand University of Technology. And we have a tied second runners-up, Dina Hussain from Washington State University and Xiaofan Yu from University of California, San Diego. Congratulations. So Valen and Artem will represent SEEKBAD and the community of embedded systems to compete in the ACM Grand Finals, and you will be contacted by the ACM headquarters. Now I move on to the Tiny and Fair ML Design Competition Awards. So we have 2 tracks. In the segmentation track, which is the low power computer vision challenge, we have the first place Model TC team. It's a mixed team from Tsinghua University, China, Max Planck Institute for Informatics, Germany, and also Model TC from China. And then the best accuracy is the team AJet Rock team from the Media Group China. And the best execution time award goes to eNote team, which is eNote.ai from LU. Congratulations. Now we move on to the classification check. So the first place is from Rutgers Efficient AI, University of Rochester. I believe it's Rutgers, right? USA. And then the second place, Sustainable Computing Laboratory from University of Notre Dame, University of Pittsburgh, and also Dos Pueblos High School from the US. Then the third place goes to Intelligent and Robotic Systems from Sun Yat-sen University in China. Congratulations. Okay, so the winners, please, those who have been announced, please come onto the stage. Yeah. As the winners come up, let me finish the award. Yeah, okay. Right, okay. Okay, right. Okay, maybe I announce again. So segmentation track, first place, please first place onto the stage. Yes. So the rest maybe wait a little bit over here. Okay. And so segmentation check, first place onto the stage, please. Yes. Yes, please.
Sorry. Not that that we didn't get time to do it. But the other two.
So these three together. Okay. Segmentation check, best accuracy team. Okay. Then best execution time team. Yeah, or maybe together.
Because there's other team members, they couldn't make it, to do very equal and they want them to be here. So let's give everybody a round of applause.
Okay, so classification track, please come onto the stage. First page, this Rutgers efficient AI, if you are here. Second place, sustainable computing lab. You're not here. Okay, please. Third place, right. Oh, second place, right. You, yes, please. Third place, intelligent and robotic systems. Yes, please. Right, then the embedded system software competition awards. So we have 3 awards. First of all, ESP, open source platform for the design and programming of heterogeneous SoCs. The second one is HybroGen, compiler for innovative interleave execution and compilation scenarios. And then Zone Trace, a zone monitoring tool for F2FS on ZNS SSDs. So if you're here, please come onto the stage. Congratulations. So SRC winners maybe also come onto the stage and take a group photo. So the plugs will be shipped to your addresses. Yeah. Thank you. So with this, I'm going to wrap up the award ceremony for the competitions. So as the overall competition chair, so in all these 3 competitions, we receive about 800 submissions. So I would like to thank my co-chairs, Wei Wen, who couldn't make it, and also Ganapati and Bresh for organizing everything. Thank you very much. So I think I'll pass the mic to Alan. Right.
Thank you. Okay. So I'm Alain Giraud. Okay, I need, yes. Okay, and so I was this year the Vice General Chair, working with Sharon and with Heiko for the organizing this conference. And I will take this opportunity to thank them again, because Sharon and Heiko have put an amazing work organizing all this. And you can believe me, it was a huge work with all the team and impressive number of emails. So thank you again, Heiko and Sharon. You will receive in a few days at the end of the week a survey. Please fill it out. It's important for us to improve the conference over years. And after that, I'm very happy to announce the location for next year ESWEEK. So it will take place in Raleigh, in North Carolina, in the US. So you probably are all aware of the fact that ESWEEK has a rotating scheme where we alternate between the US, North America. So we've held ESWEEK also in Canada and the US, Asia and Pacific, and Europe. So this year is Europe. Next year is North America. So it will be Raleigh in North Carolina. I will be general chair. My vice chair will be Kei-Wei Kuo from Taiwan. And the local chair is going to be Frank Muller from North Carolina State University. So this is the place where it will be located. It's inside what is known as the North Carolina Research Triangle Park with three famous universities. You have Duke, NC State, and North Carolina at Chapel Hill. Okay, and with that, I'm now very happy to announce and present our keynote for this morning. So it will be Professor Lothar Thiele. So he's professor at ETH Zurich. So his research interests include models, methods, design tools for the design of real-time embedded systems, sensor networks, and bio-inspired optimization techniques. He has held many positions in service to the community. He has received many awards, and he has advised an impressive number of PhD students. Some of them are even in the room. They will recognize themselves. So Lothar has made many very interesting contributions to the field of embedded systems. There are too many to cite, and they are used by many people today. I would like to emphasize a few of them. So people are probably aware of all his work on energy optimization with DVFS techniques for real-time systems. He has also made contribution on network calculus. But when I look back at my papers and I checked which is the paper from Lothar I cite the most, it's another one. So it's a very interesting paper that I guess not many people in the room know. It's about the generalization of the epsilon constraint method to generate Pareto front. And it contains a very interesting algorithm to generalize this epsilon constraint method in n dimension, and which is not at all trivial. So, okay. Thank you, Lothar. And he will present a work on the quest for resilient embedded systems in the area of machine learning.
Same thing. Change the slides, yes. Yeah, that looks good. Okay, thanks a lot for the kind introduction. And I'm happy to say a few words about what interested me in the last few years, and where I see what will interest me in the future. And maybe you share this, maybe not, so we will see. So the title is Resilient Embedded Systems, and I will start a little bit from predictability and then go to what is happening in the area of machine learning, and both about half of the talk. The title contains embedded systems. I think we all know what embedded systems are, but this is the special kind I'm usually looking at. So we have an embedded system that does the computation, reasoning, deciding. It's observing and some sort of an environment, and then sometimes also influencing the environment if you think of control or feedback or whatsoever. And then what is resilience? Resilience is related to capability of the system to react to unexpected challenges or changes that are for the system itself unexpected. And the main characteristic is that the system should recover quickly from these unexpected changes. Of course, if you do this formally, you should define what does it mean, unexpected change, what does it mean, recover quickly. But this is what I understand as resilience in the talk. So I looked a bit at the history. I remember still 2001, embedded software first conference, then ESWEEK. And of course, everything related to predictability and resilience was always in the core of the conference. And this is just something from 2006. You see all the terms you would expect: real-time scheduling, worst-case execution time analysis, also false and functional correctness, and so forth. And so it's not a new theme, resilience. It has been in the conference for a long time. But the main focus at that time was more on end-to-end predictability. That means that you would like to prove before the deployment of the system what are its properties, even under some non-deterministic environment. So it was end-to-end properties, possibly in the functional sense, but lots of work also in terms of timing, real-time properties, just to name a few. And of course, there was enormous progress in this area, and it's still going on, as we have seen in the last days, for as well real-time properties, but also functional correctness. In various computer architectures, important for embedded systems, single core, multi-core, and so forth. People have been, in the next category, talking about predictable computer architectures that try to remove interference between activities by design. Same for network architectures and protocols. And of course, finally, lots of formal methods related to worst-case execution time analysis. You know that models of computation, synthesis from formal models of computation to provide guarantees, and so forth. So just to illustrate, usually what you looked at least in the area of timing, predictability was some interference, either self-interference, things that happen through various tasks and packets interacting on the network or on the computer architecture, but also input uncertainty. And under these uncertainties, you still wanted to have some deterministic behavior in terms of timing. It was in the core of many of the work. Yeah, the next slide is a little bit dangerous because it makes a very simplified view what actually happened in this area of predictability and especially also timing predictability. Somehow the concept is usually you define an abstraction of the system, whatever this abstraction is, the elements of what you're working with. For example, what is a task? What is a runtime? What is the interaction between tasks? What about scheduling disciplines? In the next step, you define boundaries, right? You say, well, for example, my execution time is always below a certain number. Interaction is using whatever fixed priority. And then under this assumption, you compute bounds on relevant quantities like response times, right? And if these bounds, if these bounds are somehow violated, then you don't know what is happening, right? So if the system goes out of it, well, I don't know what is happening. These bounds could also encompass, of course, things like failures of nodes, but still, if a failure, if you go out of the bounds, more failures happen than just one, or something else happens, well, you don't know. Okay, so of course, we know that already many years ago, but possibly increasingly, this approach is a little bit has some challenges, right? Things are getting more complex. The computer architecture is getting more complex. You have multi-core with very complex interactions. So the abstractions you do are increasingly coarse. So what you get as a result, finally, is possibly far away from what you really can observe because it's so hard to analyze this. And of course, something else that is in the core of the second part is single processing algorithms are increasingly complex. And in the community, there's not too much going on so far on looking also on the computation and the signal processing itself. It's more on the platforms and the software and the execution and communication. Yes, you have an uncertain environment. Wireless communication is more used between nodes in all sorts of environments. And yes, wireless communication is much more fragile than what you have in computer architectures in terms of failures, link failures, and so forth. And of course, you have required adaptive behavior. So in order to look at this, it's also some diagram I also used before a little bit to show where I think there are difficulties and challenges in the approach, right? So you start with a concrete problem like multi-core, please let me know what is the worst case response time of a task, right? And then you try to compute this or to test this. And if you try to compute this, it's messy and infeasible because it's such a complex system. So what you usually do is you do an abstraction. You forget certain aspects, right? In order to make it an elegant and solvable problem. For example, you neglect interactions on caches, on shared buses, whatever, and then you do nice theory, which is very helpful because you get elegant results and lots of insights into the problem. And this helps a lot in order to design better systems, to better understand interference and so forth. But then there comes a major step, right? You would like to now understand what is the actual solution to my problem. So you need a concretization. Okay, this is a little bit taken from abstract interpretation, I know. So you do a concretization, and then you see, well, the bounds I have for individual, let's say, execution times on cores and so forth are so coarse, at least if you would like to be safe, that the final result is not so useful anymore, right? And this is the game you're currently playing with, and maybe to try to find a solution. Now, one solution, I think, again, it's again because it's simplified diagram, a little bit a difficult picture, but one approach is mixed criticality and mode switches, right? I think it's usually interpreted in a little bit different way, but it solves somehow a little bit the resilience problem. Why? Because what you do is you still have the internal or the starting point giving bounds, right? But then you say, let's suppose that I violate these bounds, right? Then I have a new onion like a surface, right? And then I'm the next one. Your requirements are a little bit relaxed, right? And of course the guarantees are smaller, but you can still give and provide formal guarantees. Okay, and then you may do this again and then again and again. And of course, what you need to take care is if you go from one to the next one, right, that you do this carefully and you need to detect this violation. Possibly you need to reconfigure, adapt the system. Remember what I thought about resilience. And then, of course, you need to hopefully go back if it's safe to do so. Right. So this is something like an adaptive behavior that reacts to unexpected challenges and changes a little bit what you can guarantee. And I think these methods are very, very successful and useful. So now let me get to the second half of the first part, right? Where I talk a little bit about resilience and what we did in one of the areas. Just why do I talk about it? Just to be a little bit more concrete, and because I'm still excited and like what was happening there. And then I go to the area of machine learning. Okay, so now resilience, it's not only related to internal interference and questions, but also to the external world, right? If you embed a system into the physical world, there are more and more other sorts of challenges that come from outside. Like if you have, let's say, a server or a base station where you collect information, Then you may have temperature, aging, physical stress, faulty behavior, whatever. If you look at the wireless network, you have radio interferences. Things are very fragile in terms of communication. And of course, sometimes nodes fail, not because someone is hammering on them, but possibly energy is gone. So let me use one example on resilience related to the communication. I know it's a bit further away from what many people do here because we are usually talking more about computer architectures and software, but let's look at communication, wireless communication, because it's an area where you have lots of changes and faults and things are going forth and back. So now let's suppose that we have two, okay, there are, if you look at this, each dot is a node. They are locally connected in order to save energy. That's also what we use in our installations. So it's not a simple star network where nodes communicate only to one. And now you have two communications. This example from A to B. Actually, what you may do is you may define a routing path and also one from C to D. There's no interference. You could even prove real-time properties because nothing is changing. You could give bounds on the individual, let's say, delay and transmission times. Okay, let's suppose now a failure happens. Node fails, link fails. Then, of course, what needs to be done, you need to reroute. Okay, and now you see after rerouting, things change a lot. What you see is, well, you have C to D, A to B, there's interference here. So you see two things. At first, the guarantees do not hold anymore. The second one, which is extremely ugly if you try to prove something, the second point is that you have very long state dependencies. A decision you do now has a very long-term influence, right? Because if now something happens in addition, okay, this fails or this fails, this is the starting point, right? So whatever you did and decided, and this is almost impossible to bound, right? There's not much you can do. Okay, so you have link failures, node failures, traffic patterns, and now you can identify two problems. The first one has been, at least to my understanding, relatively nicely solved a few years ago, and the second one I just would like to shortly talk about. The first one is, well, you have this non-deterministic interference. Okay, you have here a path and here a path, and depending on the traffic pattern, there's interference, and this is very hard to bound. No chance to do any sort of real-time computation. The second problem is coordination. In order to determine the routing paths, to organize everything, nodes should be coordinated. Okay, and if coordination fails and coordinators are not there anymore, then things will also go wrong. Okay, so the first one I will not talk too much about because, as you see on the, it's already pretty old, right? It changed the way how people do low power wireless networking tremendously, right? Because it was the first time that you could really provide guarantees, and it's a very energy efficient protocol. What is the basis? The basis is what we all know about, how to avoid interference by partitioning, by partitioning in time. Then this is what is happening, right? So the communication is not just unorganized, okay? It works in rounds. Each round has slots. In the first slot, only, let's say, node N1 is able to communicate, like in a bus. In the second round, only node 2, third round 3, and so forth and so forth. And finally, there's a coordination that collected all the traffic demands from the nodes, decides on a schedule, distributes the schedule, and then there's an extra. Perfect partitioning in time. And due to some interesting stuff related to let's say wireless communication, this can be done extremely efficiently. Okay, so this is the first part, but it's not resilient in the sense that there is a coordination failure. So what happens if the nodes don't know what to do when the next round starts? No synchronization. So there are classical approaches that are very complex, and They are used in blockchain and so forth, Paxos. So what you do is, if you have a coordinator and this one fails, okay, this is what you see here, someone new coordinates, right? So you just select another one. But it's not so simple because nodes are unreliably connected. No one knows what is happening. Did the coordinator really fail? But possibly he was just sleeping for a moment. Okay. Then suddenly you have two coordinators and then the chaos starts, right? So our dream was now different, right? To go to this to a completely different angle. What about a real democratic system? Everyone coordinates. Okay, everyone has the information to understand how the next schedule will look like. Okay, a completely system without any central organization. Okay, everyone coordinates, everyone determines the schedule, and the schedule is the same for everyone, so no interference. Is this possible? Is this feasible? And actually it is, and you can prove for the protocols whatever or what is possible, right? So it is adaptive. Nodes can change their traffic demand and the system behaves correspondingly. There's probably no interference. No packets on the whole distributed system will ever interfere, right? All is the same information and there's liveness. So after a certain time, when you change things, you can go back to the usual and normal behavior. So I thought, should I go further? Yes. And I just explain in a few minutes how it works, right? So you see where this is, right? This is the conference, okay? And I think we have central coordinators, right? Sharon and Heiko, so everything fine. But there's of course a problem. We have dinner, okay? And in this case, we have buses, right? And we all would like to somehow join dinner and use a bus to go there. So it's a typical scheduling problem because bus 1 and 2 and 3 leave at different times. We would like to know when to enter the bus. And of course, organization is horribly unreliable, right? So as we know, okay. So we don't want to rely on you. And how to do that, right? And you understand we are the nodes and this is the scheduling and our demand is we would like to go for dinner or we would like not to go for dinner. And so these are, okay, these are the members of the conference. And of course, we are also talking. So this is somehow the communication that is happening. So what is the principle? The principle is the scheduling algorithm is known to everyone and it's deterministic. So you order all the people who would like to be in the dinner alphabetically, and the first 10 go to bus 1, next 10 to bus 2, next to bus 3. So the information you need in order to do the decision is who would like to go for dinner. Okay. So how does a protocol work, right? Every one of us has a list of friends, okay? I didn't use the real names because, okay, I had to sign lots of things for the talk because it goes somewhere public, and so I didn't use real names. But let's say Olivia has a list of friends, and for some of them, she knows who will attend. And also, Liam is a friend of Olivia, or she knows him, and he also has a list. It's of course different names, different information. So what is happening now is Liam provides the list to Olivia, okay, and then Olivia joins these lists. So it's not only friends, then also friends of friends, okay. And also, she also joins who would like to go for dinner and who not, and so forth. Okay, then the list is a little bit longer, okay? But there are still some question marks, so she cannot determine the schedule, right? Because there's still this question mark here. Okay, so it goes on, she talks to other people, and this goes on, and it goes on, and this goes on. And once she has something that is called complete information, so the list is complete in the sense that all the friends of friends she met, she knows whether they would like to join for dinner or not, then this is called complete information. It does not mean that all the people in the whole whatever conference are on the list. Just those she met or where she met friends for friends, this is complete. And then she knows how the scheduling looks like. Now, but of course there may be a problem is maybe others have different lists, right? Do others have different lists? Maybe, but actually no. You can show with some small technical constraints that everyone who has a complete list has the same list and table. It was at least for us surprising, but it's very helpful because now everyone can understand for itself. Every node can understand, well, do I have enough information to compute the schedule? If the list is complete, yes, the schedule is I can use the schedule and all the schedules are the same. So I can follow, I know which bus to take, and I could even post the schedule somewhere, and those who have not complete information yet can look at the schedule. No conflicts because the information is the same. And this is what can be used actually. And it's in this sense also implementable, which was interesting enough for us. So you can implement this on the nodes, in this sense, embedded systems that are communicating, and you can induce failures. And of course, you can compare what is happening with other systems. So if you use a system that is not resilient for faults, well, if certain faults happen, you, especially if the coordinator fails, then the system will stop for some time, needs to do exchanges, information, whatever, find a new coordinator. And in the other system, even if multiple failures happen, there's a short time where things are less optimal in terms of packet reception rate because the system needs to adapt. But after some time, it goes back to normal. Okay, and of course, the question is, if you do implementations, is this a lot of overhead? No, it is not, because the protocol can be implemented very efficiently with typical primitives that you have in wireless communication. Okay, so it's just one example of resilience where you see adaptivity, failures in a very complex environment that is very challenging. Okay, now the title means from predictability to machine learning, and this is the second half of my talk. Now, what are the challenges? I talked a bit now about the two challenges on the bottom, that is uncertainty environment, wireless communication, and the adaptive behavior. And now I talk a bit about single processing algorithms and the challenges we have seen and what can be done. Now, this is again the same picture, but a little bit more detailed. We have embedded system, of course, sensors, preprocessors, and so forth. That's sensors. Then there's some communication going on, which I will not talk again about, okay? And then, of course, there's a question of extracting information to extract knowledge and to predict, decide, and control. In both cases, at least in the projects I will shortly discuss now, we use machine learning as well in the initial phase, sensor preprocessing, classification, and so forth, but also in the extracting information phase. And yes, what I will do now is I will quickly say which applications we are looking at, because we are somehow two-sided in the research. On the one hand, we try to understand formally what is going on, but also trying to have some serious application areas where we work together with people, in this case, from environmental sciences. So what we do here is we equip mountains, but also other areas with sensor networks, long-term observations in order to detect what you see here is debris flow and also rockfall. The interest from geophysics is to understand what are the geophysical processes, usually due to global warming in high alpine areas, permafrost, but also other sorts of reasons. And the other purpose why we do this is to pave the way for early morning. warning, right? So that you can warn if these things happen. So this is one of the application areas, and we have been equipping. Mainly, the work was done by Jan Beutel, who has now a professorship in Innsbruck. And we have been equipping various interesting mountains in Switzerland and also France with these sensor networks. And how do they look like? Well, they look like the figure I had before, right? So you have sensors. They are locally communicating because you would like to have batteries that last for 10 years and more, because you don't want to climb up always. You have a base station on the mountain, and you have backend data server in order to do large-scale processing. So this is one of the application domains we are looking at. Now you see here AE. What does it mean? Acoustic emission. That will be important because it's one of the examples I take. Recently, we have been equipping more and more sensors with microphones and geophones, because mountains also make noise if they don't feel well. Okay. And this is a very important sensor information that is used by geophysics to also understand what are the internal processes. The second area we have been working at seriously is air pollution, also in environmental sciences. We have been equipping trams and also other locations in Zurich in order to understand air pollution, distribution, sources, and so forth. It's not so interesting. Zurich is relatively clean, the air, possibly also in Hamburg. But there are many other areas in the world, in Europe, in US, in Asia, where air pollution is actually a problem. So we collaborated a lot with colleagues in China, Beijing, more than 1,000 low-cost measuring stations in order to get lots of data to do data analytics and try to understand how is pollution distributed, what is the relation to the weather, sudden changes, when do we expect sudden changes in the air pollution, and so forth. Okay, but also doing control using water spraying. In certain areas, they put water sprayers and they would like to switch them on and off in order to reduce locally the air pollution, for example, around schools. Okay, so that you know where we come from, right? And possibly have a little bit trust about what I now tell and say what I think is interesting. So now let's look back to the figure we had, the process, and then the various stages. Now, why do you do processing very in the let's say the embedded system close to the source? Well, you need to do sensor calibration, anomaly detection. You do classification. We will see examples of this, and also sensor fusion. That's something that is happening close to the source for various reasons. One is definitely bandwidth, energy, because if you, for example, in acoustic emission, you cannot transmit the whole acoustic signal stream over a low power wireless connection. And there are many other application areas that I only know from the name, right? And we don't have lots of experiences, but it looks like that in these areas, you also have lots of demands for doing local processing. Now, what is resilience in this case? Okay, you may think of various things that you would like to be resilient against, attacks and so forth. I use a special direction, and it will also lead to something. So the main thing what we have seen in our area is you need to do a personalization of the signal processing in the nodes. Okay, why? Because they are put into different environments. Every node is in a different environment. And you need to adapt what is happening in the node depending on this environment, right? You have different couplings to the signal source in case of acoustic emission, different lightning conditions. If you do biometric stuff, you need to adapt this to the people, and so forth and so forth. And you have this not only statically that you do it once. In other cases, you have to adapt continuously. For example, sensors also degrade, also biosensors degrade, and also the sensors we have. So there's aging, there are changes. You have something that's called changing cross sensitivities, because these sensors are not just specific for one, let's say, pollutant, but also cross-sensitive to others. And this is also changing over time. So you need to change and adapt the processing that is happening in the nodes at least once at deployment time, but also during operation. And yeah, just two examples. Seismic sensors, I mentioned it already. We use acoustic sensors and geophones in order to understand the environment. And why do we need pre-processing? One reason is the mountains are not the only ones that are making noise here, right? But there are also other people around and trying to climb up the Matterhorn, right? So they're also making noise. And this is wherever you put the sensors, there are always people around and something happening. Now, what could you do? Well, you could always transmit the whole acoustic signal to the base station, but it's impossible. So you need to do a classification on the node in order to exclude all the sources of noise that you're not interested in. And we use machine learning because it has been shown to be better than other methods in this context, in order to classify mountaineers, helicopters, wind, hail, and so forth. Just to remember, why don't we just transmit all of this to the base station? Because we would like to have a very long life. In the other one, where you look at debris flow, as you can see here on the figure, it's the same story, right? We have acoustic signals, but we need to personalize the sensors because they have differently mounted to the ground, different distance from the debris flow or the channel where it will happen and may happen in the future. So all here, if you do then classification without any sort of resilience against these local changes, it will not work, okay? So the features you extract are not the ones that you use. Okay, so if you don't do anything, there's no resilience against sensor drift, local system environment, acoustic coupling. And similar things may happen also for different scenarios. Okay, the same with pollution analysis and control. I mentioned this already. The sensors that are deployed actually have low-cost sensors. They are aging, they have drift, you have cross-sensitivities. And if you don't take this into account in the way how you use the sensors, the results are not useful because you feed your overall analysis tool with wrong data and you can forget about it. So this is also necessary to also adapt this continuously. Okay, so now machine learning, right? Of course, you could use various ways of signal processing in these sensors. And it may be that one of these nice methods to do regression or classification are helpful. Right? And in our case, we investigated several possible other methods, and it looks like they're also helpful in signal pre-processing and processing. So just one example, cross-sensitivities of sensors. You can do classical regression, as you can see here, in order to improve the relation between the measurement and the reference. You can do machine learning in various forms. Simple ones, just replace linear regression by some nonlinear function you learn, or doing more complex with some transformer structures, where you also take the whole stream of measured sensor values into account. You get much, much better, right? 20, 30, 40% better. So it shows this. Now, yes, what can you do? Okay, there's all this area of TinyML, okay, and we heard in the awards lots of stuff. If you look at the conference, many talks about moving these complex algorithms to hardware and software and optimizing this in various ways. Okay, this is something that is going on since some time, and I think also very extremely useful. But are the results then resilient in the sense we would like to have it? Not really, but what you need is that you also do local learning and adaptation, because otherwise you have a fixed system. You need to somehow transport the new data, even if you would like to relearn via the network to some host, you need to relearn all of this, you need to feed back, okay? So you need that the systems locally are able to adapt to their environment. And this is an interesting area, and I looked a little bit through the proceedings also here, and there are some papers related to it, but not many. And the first ones, at least to a relatively relevant part of the literature, appear in 2019, a few 2020, a little bit more in 21, many more in 22. It's something that gets more and more attention, and I think it's very relevant, right? Because it's extremely demanding, right? And has many aspects. So I find it a very exciting and interesting domain to look at. And I will, in the last part of the talk, to go a little bit in detail what has been done, what could be done, just to share a little bit what I think is interesting. So, of course, there is a major difference to standard machine learning, right? The communities are different, and unfortunately, in many ways, they don't understand each other, which is a plus, but also possibly a problem. Of course, we have resource constraints, so you could, of course, either use CPUs, go to ChatGPT and use lots of energy, or you could go to the extreme scenarios where you have something like microcontrollers with a few megabytes of storage and memory. And there's also the middle area where you have mobile phones that have a little bit more of computing power. My take on it, it's just a personal view and maybe completely wrong, is if you try to get something scientifically interesting, you may go to the extreme situation. The middle ground is a little bit in between. So I like to go then to the extreme and to find out what happens there. Okay, so what I discuss now is more related to the, let's say, extreme, doing this on relatively small and very low power systems. But of course, there are many other differences, as you of course know. We have a large diversity of hardware software architectures. We can even do specialized hardware. We have a trade-off between demand and quality, right? Not like in this area, the better the quality, the better it is, but you also have to satisfy the constraints. So maybe also classical algorithms are good. Okay, classical algorithms to do classification and regression. This has to be looked at case by case. And we have a large diversity of application scenarios, which is also a problem, as we will see later on, in terms of benchmarks and something to compare with. Right? So there are some good things and also some problems that await. So what I do now is to go through a small set of scenarios, just that you understand a little bit better, at least those who don't know, okay. What are the challenges? What is interesting? What do I find interesting in these challenges? So the first scenario is you don't do anything on the node, right? Okay, everything is done somewhere where you have enough power and energy, right? So this is the typical scenario. So you do this is inference, could be also regression. So I don't put both here. So inference is also regression, could be also integration, but not only classification. Then you have the basic training, which you do possibly once when you install the system. And then you have update training when you continuously adapt to the environment. And all of this could be done at the host. Now, in terms of communication, I simplified this diagram a lot. I only talk about data, but there's also other stuff that needs to be communicated, like the labels and the classes. I just ignore this here. Okay, so but what is happening, of course, there's a high traffic demand. Whatever the node gets in terms of input during operation, it needs to go to the host, communicate it. It takes energy. The communication should be reliable, timely, whatever, right? So this is the disadvantage. But also, if you do updates, you need to communicate whatever you got as new information. You need to move this to the host so that the host can do the update. Yes, now the first thing that many people are dealing with is the centralized training. So you do inference on the nodes, right? So, but the training is done completely on the host. Okay. So what you don't need to do is, in this case, during operation, to communicate the data to the host in order to do the whatever inference regression here and then give the result back. All of this is done on the node, but training is done on the host. If you have 1,000 hosts, nodes, then you need to do 1,000 trainings for every node, and then you transmit the model. And this you see here, you need to transmit the basic model to the node, but also every updated model. So what you see is, what are the difficulties? The challenges are, the first one, to do this efficiently. As I mentioned, lots of work is done here. Tremendous amount of papers appearing here also in the conference. But you need also to talk about the model, because the model may be very big. So to always communicate the model, that may be also lots of communication bandwidth. So the typical approaches, if you go through the conference, for doing this efficiently, is parallelization, quantization, pruning. We had several talks also on providing proofs that the quantization doesn't do any harm, specialized hardware, optimized software generation, finding neural architectures or architectures for machine learning that are good and not too resource hungry so this is the simplest sub-scenario, which is the one that is definitely not resilient in this sense. This is train once and deploy everywhere. So you train the model on the host once, you do optimization, quantization, pruning, you evaluate the model using some benchmarks, some data you collected, and then you move the model to the microcontroller where you get the sensor data, you do the model inference using the model you just got. Okay, this is very established, and there's this TinyML community that is dealing with this. Now, the second problem is how to compress the model, right? Because model may be big, depending on, it may have thousands of weights, and you need to all move this via low power and low energy link. What can you do here? And just one thing we have been doing, but there are many others that do similar stuff, is the following, right? Think these models have some degree of redundancy. So why always move the complete model to the node? Why not just moving what is important to the node? Okay, so the process here works as follows, okay? You get new information to update the model, and then you optimize this on the host. You get a better model, right? That now also takes into account the new information. Then you argue a little bit about sensitivities and so forth, and understand, well, in this model, I changed only 5% or 1% of the weights. The others could stay the same. Okay, so you get this information, and then you build a mask. After building the mask, you are here, and then you only optimize the weights that you thought are important. Let's say only 5 or 1% or less than 1%. And these are then transmitted to the node. So instead of transmitting all the new parameters of the algorithm, you only transmit the parameters that are relevant. And by some mechanism and analysis, you understand which ones are actually relevant. And you see, depending on what do you do, and less than 1% or 2%, only 10% of the weights need to be transmitted. But there are many other methods also. You can use pruning, whatever. They're all the same. You try to compress somehow what you transmit by understanding what is changing and what is not changing. Okay, now we come to the major scenario, scenario 3. Okay, scenario 3 is you do all the updates also on the node itself. You do only the basic training on the host, And the updates are done locally because you do not want to transmit the data you need in order to update to the host, because that's too much, right? So the node now is not only doing inference or regression, but also updating the model. Now there are three major possibilities that you can use. One is called continual learning. You do this for every new item that arrives, you do an update. And what is the problem here? It's like with humans, like you have only a restricted amount of memory. Okay, you learn new stuff and forgot the old stuff, right? It's just gone. And this is also happening here. Okay, you learn new stuff, and the old things that may be relevant in the future are just gone, right? Because you override. It's called catastrophic forgetting. There are techniques to deal with this, mainly storing important old information and then replay locally on the node. Okay, and learn also not only with new data you get, but also with old data. And this needs lots of memory, and there's also some work available in how to reduce it. Next one is called either transfer learning or meta learning. What you do is you get a model and you update this locally, but possibly only once, or only updating certain parts of the parameters. So what are the typical solutions and where are the problems? The one problem I talked about was this catastrophic forgetting. Again, what is the idea, what most of the people use, and also people start to use in embedded systems, is storing some of the old data you used for learning and then replay, right? Okay, that's one way people do. What else can you do? Yes, you can use simpler machine learning models, simpler learning algorithms. It's a very wide open area what you can do in order to improve what is happening here currently. One of the major problems with adapting the model is, what is the algorithm we are using to do this? Usually the algorithms that are used nowadays are based on gradients. So you compute gradients in order to understand how to change the weights so that the system better fits, right? It's like linear regression. You get new data and you need to adapt the regression surface. Now here you use gradients because it's a nonlinear system. Computing the gradients is extremely lots of effort in terms of memory, because you need to remember things from the inference phase. And there are many gradients and the computation is very demanding. So there are, again, lots of things you can do, like pruning the gradients, okay, doing this dynamically, right? Recomputing gradients, right, by trading off computation versus memory. So many things you can do, and some of them are listed here. To me, it's a wide open space of lots of nice things to be developed and to look at. Just one thing we have been doing, just to say that we also have been doing something, right? So this is called meta training. The idea is the following. You update on the nodes, but the model you start with is a useless model, okay? It's not good for anything. The only thing it's good for is you can quickly learn to everything you are interested in. So it's something, a model in between, and you know it's easy to learn if something happens in the environment. So it's a good starting point to learn. It's called meta learning. And this is what we do, learning such a model on the host, moving this to the device, and then updating this model. Yes, and then we have the problem of gradients, and you need to prune the gradients. We do this dynamically and statically, but at least it's not much, but you are able, without losing any quality, reduce memory and computation by a factor of 3. It's not what you want, but at least you can see that you can achieve something. Okay, I don't, due to the time, I don't say anything about federated learning, but it's another way what you can do. I would like to finish somehow with what I see as challenges in this. At first, resilience to me, as in machine learning, at least one part of it is adapting the model on the device. That has lots of interesting questions in terms of hardware architecture, of software, of algorithms. And I think it's a very interesting and challenging area, and it's needed. What is missing, right? I think in our experience when we started with this, it's really hard to start because the community is not so organized like many other communities, like the machine learning community in this area. No benchmarks, no software available, right? There were very early on papers that we really liked, great. We wanted to re-implement and trying to understand what they do. Software code not available, they didn't give it to us. Benchmarks not available, right? So what do you do, right? You start from scratch, you re-implement, and it's a nightmare, right? So this is something that is really, it's difficult. Okay, I know it's a long-standing discussion in the community on repeatability or reproducibility of results, but I think also in this area, it's really giving us a hard time, right? Software is not available, it's not put on archive, and it's somehow, it's difficult. Okay, the next one I think it's interesting is not always deep learning or these new machine learning algorithms are the best. And depending on the scenario, I think it is really worthwhile also to look at classical algorithms to see how they can be adapted, not only the new machine learning ones. So it's a similar question, but also for many of the other well-known algorithms. Yes, it's for us a lot of fun to look also at new processing models and learning principles, hyper networks, whatever you can do, and it's a lot of fun, right? So you are really starting on a relatively open space. You have a clear thing, doing regression or classification, and possibly there are other structures, invertible networks, whatever, that could help in this context. The last one, formal proofs, yes. I showed a little bit of the middle part on purpose that there are certain things you can prove if you do something on computation or communication and fault tolerance. Here we are further away, but I think there is hope also to prove something in terms of resilience and adaptation with the problems we have seen so far in terms of whatever catastrophic forgetting and so forth. Why? Because the models that fit onto these small devices are also smaller. So formal methods have a little bit an easier time to get to a solution. They may not be able to find a solution for ChatGPT, but possibly for networks that just have a few thousand parameters, right? So there's a chance to formalize all of this. And you see there are some formal proofs, especially in the area of control, right? Doing neural network control and feedback and regression using various methods. And I think there's also hope here. And that is something I think would be extremely valuable. We don't have it. Okay, so the original goal to do resilience in the way we like to work here in terms of signal processing is still far away, but I think it would be a great goal. Okay, so this finishes my talk with a few ideas what could be done. And yes, acknowledgements, some PhD students that worked on this recently on the right-hand side. And all these things here, they have been all supporting what we have been done in terms of practical applications on the mountains and so forth. Because if you commit to an application, you need, unfortunately, quite some money to do that, right? So we have been very generously sponsored by them. Okay, that finishes my talk, and I hope you liked it, and maybe there are some questions.
Thank you, Lothar, for this wonderful talk. So, questions?
Yes.
Thank you, Lothar, for a very nice talk. You talked somewhere in the beginning about both sort of models that in terms of resilience, you
Yes.
talked about how you might react to failures, but
Yes,
you also had this word predict.
yes.
And I'm wondering where this notion of proactive models, in terms of anticipating failure so you can do things ahead of time and avoid getting out
Yeah.
of that zone. So can you speak to that, and what does that mean in terms of how you do things on the node versus in the cloud or wherever?
Yes, it's. I didn't think much about it, right? If you're in the beginning, I was more talking about, let's say, the classical sort of predictability and systems. Yes, you may predict that something overruns or failure may happen, right? But I'm not so sure that it's so easy to do, right? So, because this part of research is very much related to providing guarantees. And it's been also from computer architectures, they get lots of performance from doing prediction, but to provide guarantees on the prediction and what happens later on will be very hard. So maybe there's room for research to be done, right? But I think one should carefully look at what can you prove about the correctness of prediction. Because if you do this formally and you go from one shell to the next one, okay, this should be formally correct, right? So yes, you may do this just because you think that something may go wrong, but at least if something goes wrong, you definitely should move to a new scenario. Yeah. But I think in principle, yes, predicting may be good. So we do prediction a lot in the signal processing algorithms in order to predict things, but not in this case.
Right. Thank you, Professor Thiele, for the presentation. So I have two questions, right? So the first one is on the conceptual level. So because I think resilient systems are very important, we also do some work in this direction. But how would you define resilience against robustness? Because some of the things you talk about, I would define as robustness, but I would like to have your view on this. So the first question. Yeah.
I think resilience is defined in many ways, and I think I gave just a very informal definition because it depends a little bit on what you are looking at, right? Mm-hmm. To me, these are the main things that I discussed. So there are some changes, right? And you do not encompass the changes in the inner circle, so to speak, right? On the boundaries, right? Of course, you know what kind of changes to expect, because otherwise you don't know how to design the system, right? And now these changes happen, and the main point is the system should somehow react to these changes. And the main point is what resilience means, that you go back to the usual and normal behavior in a bounded time. Right? So you should say something what is happening in between, and you should go back to normal operation. And this is also what is usually called as resilience of whatever, society and so forth, right? So there may be something happening, there's a little bit of chaos possibly, you hope that you still work, but then you go back to normal. And if you define it, you need to define what is actually what you mean by unexpected change, and also what you mean by going back.
Yeah, understood. Thank you. And a follow-up question. So is there a certain part in your work, right, which cannot be solved by investing a little bit more resources? Because I think our community, we are very good at saving resources, but sometimes our value is also sort of restricted. So I'm wondering if there is something we can do to turn something that is impossible to possible. Could you make some comments?
Of course, yes. So as you see, the software we're doing on our own, the hardware, and of course there are many things where you adapt also the hardware to be more resilient and predictable. I didn't talk about this, but the hardware is built in a very specific way that supports predictability of timing, right? So there are several processors on it, but they're interacting with a custom-made interface in order to avoid interference. And this has been even formally proven to be correct using abstract interpretation and all these things, so that we know. So this is a point of investment, because we also wanted to put some of this part of the research into the system. And the other one where we need a little bit more resources is sometimes in the wireless communication. right? Depending on the scenario. Of course, yes. What we do not do and never did, it's just we don't, it's not my area, doing really specific hardware and chips and new computer architectures. But this is a very valuable work, and I just read some papers and stuff from Luca Benini. He's doing a lot also in learning. So if you are interested in computer architectures dedicated to local learning adaptation, he did quite some work, and I think it's very useful to look at. It's not what we do. Just
So thank you. Thank you for the lovely talk. I just wanted to quickly ask you, whenever you have these nodes and they receive data, they often are extremely expensive when power is considered. So it's about 100x more power when they start to receive, because they have to wait for things to come back and receiving from other things and stuff like that. So updating is a very expensive affair. Has this been considered while learning this type of federated learning and things like that?
So this goes back a little bit to the way how we do the communication, right? So starting in 2010, 12, and so forth, there was a new protocol based on something that's called synchronous transmissions. It changed the field tremendously, and it's working a little bit different than other sorts of protocols, wireless protocols. It uses a conventional radius, but works a little bit different. So the receiving, so you do broadcasting. A node sends information and then it broadcasts to all other nodes in an extremely efficient way. You just transmit the information to the next one receives it, and then with a very short delay repeats it and distributes it again. So it's something like a very short and very intensive flood through the whole network. And this is very efficient, and there are lots of comparisons also of others to conventional protocols. It's extremely competitive, right? Because no neighbor discovery, no routing, no local state, right? So this is what we use, and therefore distributing information is very cheap and can be done, as you see, with very low overhead. So the protocol, so I think one needs to distinguish between the algorithm itself, okay, and the protocol that actually has been then put into place in order to make this efficient. Historically, actually, the protocol I was just sketching was done the other way around, right? People started from playing around with the protocol and trying to understand what to do, and then later on we had lots of fun discussing why does it work and so forth, and then suddenly a very simple principle came up. But it's dedicated to do things very efficiently. Yes.
Robert Dick, University of Michigan. That was an exceptional keynote. About the data set and benchmark availability problems. They appear mundane, but they're fundamental barriers to rapid progress on fundamental research. Yes. And the machine learning community has done a better job so far. But they do have a different situation. They have an awful lot of people working on almost exactly the same problem. So they can amortize the cost of building these data sets and benchmarks. We're fragmented. Some of us are even extremists, right? So we're working on the farthest you can go because we think that's going to reveal something interesting about the future. But it also means that far fewer people are working on each one of these benchmarks or data sets. How do we solve this?
Yeah, you are right. Yes, I completely agree with your statement. I think it's in a certain sense also the willingness to put a little bit of effort into what you do and to just put the software and the benchmarks online, at least the ones that you use to produce the diagrams in the paper. Because at least to my understanding, otherwise it's like a proof or a hypothesis, like a theorem or hypothesis without a proof, right? If you just have the diagram to say, well, this is the data set I get from company X and I use this and these are the results, I have no idea whether they are true. I cannot see how it works and so forth. At least this should be mandatory for the major part of the paper. I understand that sometimes because of certain reasons you're not allowed to publish the data, but at least the majority and the main part of the data should be able for other people. Right? It's additional work, I know. And of course, the machine learning community, it's a little bit easier for them because they don't have this diversity of architectures, of computer architectures, of scenarios. So for them, it's also a little bit easier, right? It's not an excuse, it's just an explanation.
Okay, so we have time for one last question, Luca.
Yeah, I had two, but I'll just do one.
Well, then you can.
Can you hear me? Yeah. So great.
Yeah,
talk. Thanks,
yeah,
Lothar. I guess I had two questions. But the first one is one of the last slides when you show about learning on the edge, no?
Yes.
And you said the model is really not a useful model. It's just a meta model that is a great starting point to learn locally.
Yes, correct. Yes, it's called meta learning.
I assume that, yeah.
It's called meta learning in the
meta
community,
learning.
yes.
And yeah, no meta model, meta learning. And you said that starting learning locally. So if I understood correctly, the single node learn by itself, not even talking with the local nodes, or maybe I stand corrected there. But what is, if you can clarify that, so how that learning happens, and what is so special of this model for meta learning that is not good, but is good to learn on top of that? I didn't get the intuition.
Okay, there are two questions. The first one, what is this model that you start with when doing meta learning? So it is optimized. So what you do is you have an idea what kind of scenarios to expect, right? So you should have some idea in which environment you are, and let's say different mountings to sensors, you do augmentation of data sets, whatever. And then you learn a model that if you confronted with one of these data sets, it can quickly learn a model that is very good for this specific data set. So you do not, the objective of the learning is easy to learn. Right, so it's not good for something direct, not good for any of these data sets, augmented data sets you have, but it's good to go to one of them, right? So it's a different learning objective. And the other one is what happens on the node. On the node, you get usually only a few samples of the data sets, possibly 5 to 10, and then you adapt this easy to learn model with 5 to 10 data. You apply and you learn them, but not hundreds or thousands or millions, just 5, 10, not more. Because it's an easy to learn model that encompasses almost everything. You just need to reconfigure it. But the learning itself uses the conventional mechanisms using gradients and so forth. So therefore the methods are useful to prune gradients and so forth. So this is the.
It's because you have some assumption on the dynamic range of what.
Yes, the assumption of the dynamic range is given by how you learn the meta model. Yes, it's all heuristic, nothing to prove. Sorry, it's.
Okay, thank you very much. Thank you again, Lothar. So we now have the coffee break, and so remember that ESWEEK 2024 has been announced. So for next year, start working on your new paper.
Okay.